Hello, and welcome back to OC is Easy. Today, we're doing a side-by-side comparison of two fundamental tools in analytical chemistry, Dispersive IR and its modern successor, Fourier Transform IR, or FTIR. This is a perfect example of a technological leap that changed what was possible in the lab. Dispersive IR is the classic approach. It's built with a monochromator that uses prisms or gratings to separate the infrared light into a single wavelength. This beam is then passed through the sample. The issue? You have to move the grating or prism to measure each individual frequency, one by one. This leads to a few key problems. Mechanical wear. With many moving parts, there's mechanical slippage and wear, which affects calibration and reliability. Slow scan speeds. Measuring one wavelength at a time is incredibly slow. You can't monitor a fast-changing system, like a chemical reaction in real time. Signal loss. The slits needed to isolate a single wavelength restrict the amount of light that reaches the detector, meaning a lower signal-to-noise ratio. In contrast, FTIR is an engineering marvel. Instead of a monochromator, it uses a Michelson interferometer. This device splits the IR beam, sends one part to a fixed mirror and the other to a moving mirror, and then recombines them. This creates a complex interference pattern, called an interferogram, that contains data for all frequencies simultaneously. The magic is in the name. A mathematical process called a Fourier transform converts this interferogram into the final, easy-to-read spectrum. This radical change in design gives FTIR three major advantages. The multiplex advantage, because it measures all frequencies at once, it's incredibly fast. It can collect a full spectrum in a second or less, 100 times faster than a dispersive machine. This is huge for real-time analysis. The throughput advantage. FTIR doesn't need slits, so much more light gets to the detector. This means a higher signal-to-noise ratio and more accurate data from even tiny samples. CONUS advantage. An internal laser is used to precisely track the moving mirror, providing unparalleled accuracy and reproducibility. The transition from dispersive IR to FTIR is a perfect case study in how a change in engineering philosophy, from sequential measurement to parallel processing, can revolutionize a field. It made spectroscopy faster, more sensitive, and more robust. This is the kind of project management and innovation that we live for in science and medtech. If you found this breakdown insightful, please hit that like button and subscribe to OC is Easy. We'll keep decoding the technology that's shaping the future. See you next time.